Okay, first of all, let me thank organizers for inviting me to this great workshop program and conference. So today, I'm going to talk about how we define non-equilibrium phases of matter, namely how we replace the idea of gap from the pure state quantum phase of matter into the general non-equilibrium mixed state. And this is a collaboration with a very talented graduate student, Tai-Sun Yang from my group, and Bo Wen-Shi, who's a postdoc in my group. And the talk is mainly based on this archive posting. So, I mean, throughout this conference, we talked about like phase of matter a lot. And essentially, in this, what fits into this program's theme is like, we have some like quantum simulator platforms or quantum devices. And this device is generating a, set of like states, the sequence of states. And, like a certain tuning parameter is generated like psi 1, the other tuning parameter is going to generate psi 2, and so on. And our goal is trying to identify what state this belongs to, what phase this state belongs to. So in the case of pure state quantum phases, there are lots of like useful notions. Like, but now, if your device is under noise, generically it is going to generate like density matrices, mixed states, and there is no like systematic framework on how to classify mixed state, how to put a label on a mixed state. So for a Gibbs state, which is probably the most familiar kind of form of the mixed state, there is a notion of a parent Hamiltonian because it's given as e to the minus theta h. And from that, you can calculate the partition functions. And from the singularity of the partition functions, you can kind of talk about phase of matter. But for a very generic form of the density matrix, we don't have such a tool. So this is definitely the question we want to address, especially when we are simulating systems with noise. So the question is, how can we define non-equilibrium phases of matter for generic mixed state? And the short answer we provide is this mixed state bootstrap framework plus topological channel connectivity. So what I mean by this is the following. First, we came up with a new notion, a new condition that defines the fixed point of a mixed state. It's like a zero correlation length in the case of like pure state phase of matter. And second, for this fixed point under RG, whatever depends on how we define, but let's say some fixed point under coarse graining RG, we found some diagnostics that can label different fixed points. And when we relax this fixed point condition to be violated a little bit, we can show that this diagnostics stay robust. So they really serve as some kind of topological invariant, and these like conditions serve as like a notion of a gap. Because for example, in the case of Fermi Chern insulator, we know that as long as we are deforming a state while maintaining the gap, we know that the invariant stays basically the same, right? And same kind of physics is happening here. And then finally, we demonstrated that like under the action of a weak enough channel, these axioms are only violated a little bit. So essentially, this kind of conditions also has a robustness as a notion of a gap in the pure state phase of matter. So that is the short summary. So this framework is giving us basically how we can jump into the classification business of mixed state phases of matter. So when we are talking about quantum phases of matter, we are kind of restricting ourselves to the ground state of local and gapped Hamiltonians, right? And it has all the nice properties that allow us to classify phase of matter, but it also allows us to exclude some pathological examples. For example, you can always think about some weird wave function, which is a superpositions of like two different wave functions. Or it can be some wave function, which is some like a patchwork of different like phase of matter. Such a wave functions are precisely excluded by the condition that we're considering local and gapped Hamiltonian. But as I said, for generating mixed state, since we do not have a notion of a parent Hamiltonian, we have lots of problems. For example, someone can throw you some density matrix, which is an incoherent mixture of like a weird phases of matter. Like, how can we label them? Maybe we want to set some condition to exclude such a situations, right? So really the goal here in this classification business is coming up with some sensible notion that like constrain your kind of state space. And basically, when it comes to mixed state, the most important question is what properties would provide a good definition of mixed state phases. And while doing so, it should be restricting enough such that it can like exclude some pathological examples I mentioned before. At the same time, it should not be too restricted, because if it's too restrictive, it's gonna give you some like a very unreasonable kind of refined classification, right? And the result, the classification we obtain through this framework must be physically meaningful, in that it should distinguish different information theoretic phases people have previously explored. So I came from a few motivations. The first one is the protocol to prepare long-range entangled state. So by combining finite depth local unitary measurement and decoding operations, it was known that you can prepare long-range entangled state. And the question I asked was, well, what if like each of this component become faulty? Will this protocol remain stable? And I found that indeed, even when each of this protocol remains faulty, stays faulty, there is some like a threshold below which we can still extract some long-range entanglement out of this. So it seems like there is a phase transition of this information theoretic protocol, right? The second motivation comes from the very well-known example of the toric code. So when we have just a raw physical qubit, and when we decohere them, so x-axis the x noise, y is the z noise, the amount of decodable information just continuously degrade as a function of the noise. So the color plot here means the amount of decodable noise. But when we have a toric code, we know that as long as the threshold is below certain value, we can extract certain amount of logical information above which like it's gone. So there is seemingly a phase transition behavior. And if we can label each of this like a kind of maximal kind of point as some zero correlation state, and each of this star point has different classical or quantum information theoretic capacity. So all these kind of examples kind of give you the sense that we should be able to define, or we might be able to come up with some nice definition that incorporate this non-equilibrium phases of matter. I also want to mention that this kind of point cannot be well captured by some Gibbs states, like parent Hamiltonian idea. So there are lots of earlier attempts. So there was a notion of the two-way connectivity, that like two states are belonging to the same phase if they're connected by a finite depth local channel. There was this idea of the double space formalism, where you consider density matrix as some like a vector living in the double Hilbert space, and you classify it as you did for the pure state formalism. And there are lots of empirical suggestions based on the diagnostics. But the issue is that these are all kind of proxies. They are either contradictory or kind of quantitatively inaccurate, nor systematic. So I got the idea from something called the bootstrap approach, which is the following. So when we usually talk about quantum phase of matter, it's based on the notion of Hamiltonian. So first of all, when you think about state space of wave functions, they're just like a big chunk. They're all connected to each other. Now we impose a constraint that we're excluding all the states that are not the ground state of a local gapped Hamiltonian. And when we do so, this chunk split into islands, and then we can label each island as a phase of matter. But we can attack the problem in a different way, which is a wave function-based approach. We first impose some constraint that's describing the fixed point wave function under RG. And starting from fixed points, then we can allow some deformations to explore around the phase for each of the fixed points. And this is like a wave function-based way to define phase of matter without referring to the Hamiltonian. And basically what I'm going to do is the approach similar to the second method. I'm going to define the mixed state fixed points, and then I'm going to allow which deformation is allowed to explore the mixed state phase of matter. So in doing so, there are like two important quantities. The first one is a mutual information. So when we have this like spatial partition into the region ABC, or just like in the distributional sense, you have some kind of joint distribution of the variables in ABC. There is some kind of correlation between the variable in A and variable C, and that's captured by something called a mutual information, I, A, and C. So this actually upper bounds any correlation functions between A and C. So this is, in some sense, a basis-independent way to quantify the correlation, which is what we want, because under the noises, we lose the information about like specific preferred basis, right? So whenever you're talking about information theoretic phase, you want some basis-independent way. And when the mutual information is 0, it simply means that the reduced density matrix on AC just decompose into the tensor products of row A and row C. And this first gives a generalization of the idea of correlation length. And the second important quantity is a conditional mutual information. So again, this is actually the direct correlation between A and C that's not mediated by B, as this Venn diagram shows. So when the conditional mutual information between A and C is 0, it means that the correlation or entanglement between them is only mediated by B. So what it means is that, for example, if I trace out C, then I can reconstruct the entire density matrix row ABC by just acting on the region B. And this is called a path recovery map, and such a state is called a Markov state. And okay, why should we consider conditional mutual information? I mean, I was happy with just correlation function when I play with the classical systems. But actually, even for the classical systems, conditional mutual information is important when we are talking about information theoretic phase of matter. Because this conditional correlation is directly related to whether we can decode or recover a part of the system when some noise or like irreversible action is applied. So with these two ingredients, then we can proceed to talk about how we define the fixed point of a mixed state phase of matter. So in the pure state case, we had only like a one kind of quantity gap, right? But here, instead of 1, we have 3 conditions, which I label as a P0, M0, and M1. So the first condition, P0, has to do with the local recoverability. It means that when you consider such a partition where E is the rest of the system, the conditional mutual information between the rest of the system and like some local patch C, condition is like in a shielded area, is 0. Meaning that if you erase a C, it's locally recoverable. Second condition is that for any separated regions, A and C, the mutual information is 0, which just basically says that you have a 0 correlation length after a certain coarse graining. And the final condition, M1, is about conditional mutual information between A and C, condition and B, after tracing out D here. It looks kind of tricky and probably not very intuitive, but this condition is about the smoothness or uniformity of your state. So this condition is precisely the one that excludes certain pathological cases, like you can think about the wave function where in the half space is paramagnet, upper half plane is a ferromagnet. Such a wave function is some weird thing. We don't consider them when it comes to the classification because it has a domain mole, right? But that's automatically excluded from the local gap Hamiltonian condition because you can prove that such a wave function with this boundary domain mole between 2 different phases cannot be the gap ground state or not the ground state of like a local Hamiltonian. The ground state of a local gap Hamiltonian. So to dig in deeper to each of the axioms, I said that like this first condition P0 is about the local recoverability because what you can prove is that the CMI is 0, then you can just recover the erased local region C by just acting on its a small neighborhood. So this is some of the condition you'd want to require for just like topological order, right? Because you want your global topological information to be robust in the local eraser. And like another way to think about this is that this is the condition to prevent the novel information theoretic phase transitions that can happen in the mixed state setup. So let's say we have some like a charge symmetric dynamics, and our initial state is some well-known definite charge configuration, and you know the charge at each side pretty well. So the density matrix is simply represented as a product of projector on each kind of site. But which means that if you're gonna erase a certain site, then you can just like put things back without interrupting other site. But when your charge is so scrambled after the dynamics, we only know the total charge in the system. That means that if you apply some eraser on the single site, then your density matrix immediately just decohere into the maximally mixed state. And in order to recover the original density matrix, which is a projection onto the global charge vector, you have to act on the entire system. So this setup, things are not locally recoverable. And this is precisely the physics of something called the strong to weak spontaneous symmetry breaking, and it's precisely banned by this condition. So if you're interested in the strong to weak spontaneous symmetry breaking, there's a series of work I've done for the case of higher form, Ising, fermion parity, and charge U1, where in the case of charge U1, the spontaneous symmetry breaking has a consequence on the hydrodynamics. So the second condition is simply saying that you don't have a long-range order because mutual information gives the upper bound on the correlation functions. And by imposing this, you're excluding a conventional kind of long-range order state, like spontaneous symmetry breaking. In the later part of the talk, I'm going to talk about how I can relax each of these conditions to incorporate also the strong to weak or genuine spontaneous symmetry breaking phases into this framework as well. And this condition M1 is, as I mentioned, it's about kind of uniformity of the density matrix. So essentially, if it imposes conditions, your density matrix does not have a domain or wall or defect in its spatial structure. So you can think of this as some condition that quantifies the smoothness of the many-body correlation or entanglement structure. Because without this notion of a gap, there should be a way to impose some smoothness of your kind of correlation in your system, right? But if you impose just a translation symmetry, that's too much. Translation symmetry is like too much kind of constrained. So I don't want to use translation symmetry. But then this is a version of the condition you can impose to guarantee the minimum amount of the smoothness in your density matrix. And what you can infer why this is associated with smoothness is because finite depth local unitary can never violate these axioms after some coarse graining, but a finite depth local channel can violate it. Because if you think about local unitary, that's just change of local basis. It keeps the kind of entanglement or correlation structure smooth across the system. And these three conditions are independent. What I mean is that you can always find a state that satisfies two, not the other. So if you have a state with a pair of non-abelian anyons on the region A and C, then because non-abelian anyon acts like a defect, the path information is important, whether this AC is created through this path or this path. What it means is that after tracing out D, there's a non-zero direct correlation between A and C conditioned on B. So this will violate M1. The second example is just genuine spontaneous symmetry breaking, which violate M0 but not P0 or M1. And then the example I talked about, strong to weak spontaneous symmetry broken state, is precisely the one that violate P0 but not the other two. And you can show that this is, in some sense, RG fixed point, because if these conditions are imposed everywhere for any kind of small local partitions, then they reproduce themselves at a larger length scale. What I mean is that if these axioms hold for a small length scale, then they automatically hold for the larger length scale. And additionally, if these conditions hold at very small length scale with some violation, the way you're seeing is that if you're coarse graining, meaning that you merge the cells into larger cells and calculate these axioms again, the violation is getting exponentially smaller as you repeat this process. And that's usually the case for most of the physical state of interest. You can construct very pathological example where it's not violated at the small scale but violated at the large scale, but or they naturally arise at the critical point. But in most of the kind of anomalous gapped phases for the mixed state setup, such an RG behavior holds empirically. So then we can ask, what states satisfy these conditions? So all known solvable models exactly satisfy these conditions, like your familiar examples of the toric code or some exactly solvable model with zero correlation length. They all satisfy the axioms. And any product state satisfy axiom trivially. And not only the like a pure state of the exactly solvable topological orders, so maximally charged or flux P coherent quantum double also satisfy these axioms. Now, we defined what I mean by the fixed point of a mixed state. And after that, we want to move on to how to distinguish different fixed points. Namely, we want to come up with some invariant or some order parameter to distinguish different fixed points. And there are like several kind of invariant you can come up with, but one of the crucial idea is something called the information convex set. So the question you can ask for a given setup is the following. So let's say you have some giant, state, and you have all the local information in that you have a complete cover of the state given by the local patches, and you know the reduced density matrix on each of the local cover. Can you reconstruct the entire density matrix given that there's a local information? So this is really a tomographic questions, and there is a case where this is precisely not possible. And that's the case when your system is defined on a topologically non-trivial manifold and you have a topological degrees of freedom. Because local reduced density matrix, no matter how accurate they are, they can never fill some topological degrees of freedom. So the information convex sigma on the manifold M given a state sigma, lowercase sigma is defined as the following. So it is set of all density matrices that are locally equivalent to a given density matrix sigma, meaning that local reduced density matrices matches for any disk you consider. And we additionally impose that the density matrix we consider has a local recoverability, meaning that it has no kind of large CMI or local patchy between the rest of the system. And when I look at this information convex set for example, toric code, precisely the degrees of freedom not captured by local patches is quantum logical operators. So it corresponds to this block sphere. But if I have some topological state, but if the correlations are classical, then I'm gonna get this simplex with a finite number of extreme points. So when your extreme points form a continuous manifold, it means that you have some topological information and that is quantum. But if your extreme point of this set is discrete, that means that you have a topological information, but that is classical. So if you have just a quantum pure state, we can prove that under our axioms, the state you get will only have a quantum types of memory or nothing, meaning that extreme point will be always some continuous manifold. But when you have a generating mixed state, there's a possibility of having a topological yet classical memory. So you can also calculate the memory capacity, like how much bits or qubits of information this topological state can encode. And that's given by the difference between the entanglement entropy between a maximum difference between the two elements of this set. Because again, any two elements are locally equivalent. So if they have any difference in terms of entanglement entropy, it's coming from the non-local topological part. So this difference is precisely capturing that topological degrees of freedom. And what we can show is that the quantity called the topological entropy is giving the upper bound on this memory capacity. And actually, for all the abelian quantum double model or decoherent model, we can show that this memory bound is precisely saturated. And it should be contrasted with the pure state case, where the memory capacity is upper bounded by twice the topological entropy. So if you observe something where the memory capacity is between twice the topological entropy and 4 times, then you can tell that, okay, you're not having entirely quantum memory. You're having some hybrid of quantum and classical memory. And that's precisely the possibility that emerged in this mixed state setup. And now that okay, that's one example of the topological invariant, but there are plenty of others, so I want to refer to my paper. And now it's time to talk about, okay, enough for the fixed point. How can we talk about phase of matter? So in the case of pure state, we say that two states belong to the same phase if they're connected by finite depth local unitary. But when we generalize things into mixed state, the basic kind of operation is like channel. So you may think that, okay, can we simply replace the equivalence relation by from the finite depth local unitary to finite depth local channel? Can we just claim that two states belong to the same phase if they are connected by finite depth local channel in both directions? That can be one way to define phase of matter, but that shows some issue. So again, consider a toric code and two fixed point, because I call them fixed point because these two yellow stars satisfy the axioms I mentioned. So this upper right corner is a product state, lower right corner is the product of X stabilizers, including only classical topological bit. Then you can actually map one to the other using the finite depth local channel. So from like a rho 1 to rho E, this is a procedure. You start from the product state, which is a product of like pluses, and then you measure the BP, the Z stabilizer everywhere. There's no post-selection because after measuring, you just throw them away. And actually, after measuring and throwing them away, what you're obtaining is this rho E. And going from like a rho E to rho 1 is actually even simpler. You just apply a finite depth local channel, the product of like a on-site channel, which is just a reset. Just like this reset channel is just like setting every qubit to be a plus state. So okay, according to this kind of two-way connectivity, it seems like I'm identifying two states with the different topological entropy and different topological information capacity. Well, you can just, okay, maybe they're same phase, it can be satisfied, but I found this is not very satisfactory. So following our notion, like these three conditions I proposed, we define the equivalence class as the following. So we say that two density matrices are in the same phase if they can be kind of stitched together without violating axioms much. So if you try to stitch the two different phases across the boundary, you're going to develop the domain wall, and at the domain wall, you're going to violate the axioms. But if after stitching, if you can find some like procedure where you can smoothly interpolate them without violating the axioms much, you can, then we define that they are in the same phase. And according to, following this definition, we can show that the Z decoherent toric code or X decoherent toric code belong to the same phase because we can smoothly interpolate them without violating the axiom. And this way of definition gives a hint on how we should impose an additional constraint on the finite depth local channel to make it more sensible definition in this mixed state setup. So hints coming from considering the familiar idea from the symmetry protected topological phase. So in 1D, the simple product state and one-dimensional Z2 cross Z2 SPT state can be mapped to each other by a finite depth local channel, which is a product of control Z's. And on the circle, the product of control Z is totally symmetric under Z2 cross Z2 symmetry. So you may think that, oh, do they like collapse into a single phase? But that's a wrong way of thinking because actually, locally, U is not symmetric action. Control Z is precisely violating the Z2 on-site symmetries. And the way to see this is that if you truncate the action of the map, at the boundary, the symmetry is violated. And that's why U mapped here is not a valid equivalence relation when we think about SPT. So my proposal is that we should make the same consideration for mixed state because channels are weird. While the finite depth local unitary is just a change of local basis, it preserves a global smooth entanglement structure. Finite depth local channel can break the entanglement, do all sort of weird things because of the monogamy of the entanglement. Even if you like small like entangling operations can collapse the entire global entanglement structure. So you should give it some like equip it with some like feature of smoothness so that like global entanglement correlation structure is not getting violated. So that's what we mean by topological channel. If two states are connected by finite depth local channel, and if you truncate the action of the channel into a finite region, and if these axioms are okay around the boundary, meaning the violation of these conditions are exponentially small in the partition size we consider, then we are saying that such a channel is topological, and they are valid a connection, equivalence relation between two mixed states. So now, let me show you some numerics. So I have a toric code, and on the lower half plane, I'm decohering with the Pauli X noise. So first of all, I tracked a violation of this condition P0 with the different kind of rescaling parameter R of the partition size. And you can see that there's a crossing at the well-known critical point of 0.11 where the toric code is supposed to lose its quantum information. And not only that, at any finite error rate, as I rescale R, the violation is getting actually exponentially smaller, meaning that there is this condition is indeed RG into kind of zero value as long as you're deep in the phase. And we have a fraction numerics, which is not here now, but we have a numerics of the R equals 30, where basically this looks like kind of almost zero and the peak at the critical point and coming down. And what's quite interesting on this plot is that when we rescale everything with R, the violation at the critical point seems to saturate some value. And that's some mystery to me. And I conjecture that might have to do with some, disordered CFT governing this transition. And we can also look at violation of M1, which is supposed to be constant after the threshold, because since I'm looking at this at the domain wall, after the transition, you're supposed to look at the violation is just constant, no matter how large it is, and indeed exhibit the expected behavior. And the violation away from the critical point all decay exponentially with the system size, meaning that this indeed acts like some the quantity you want for the under RG. Okay, and you can also prove that if you have a violation of the axiom everywhere slightly, then you can also prove that the topological invariant we consider remains robust no matter where we calculate. So this indeed kind of plays like a gap again. And the notion of the topological channel connectivity plays really well with the symmetry. So now we can add a symmetry here. All we have to require is that on top of topological channel connectivity, requiring that at the boundary when you truncate, you satisfy the axiom. On top of that, you just required to satisfy symmetry as well at the boundary. And after that, you can talk about mixed state SPT and mixed state SET very conveniently. And now you can relax each of this condition P0 and M0 in the following way, that it saturates to a kind of constant value plus exponentially small correction. Then you can also incorporate strong twig SSB or genuine SSB, where we conjecture that if there is some Zn SSB, then as you RG rescale this partition, this violation will saturate to a log n. And finally, by relaxing M1, it's probably possible to talk about mixed state fractons or some state which is a network of defects, but that's something we don't clearly know about yet. So the final outlook is the following. So these three conditions really play like a gap in this non-equilibrium setting. And what we want is proving the stability of this gap in the sense that when we apply weak enough channel, we want this violation to stay like exponential violation. So starting from a fixed point, we could prove this, but starting from the when they're exponentially small, under arbitrary weak perturbation, this violation stays exponentially small. That's an open question. And using this framework, we could actually sort out how to define the emergent higher form symmetries, either strong or weak. And we're now wondering how this framework, which is, this framework is nice and it's not referring to parent Hamiltonian nor some underlying dynamical process. But now then the next step one can ask is whether certain how this kind of classification is related to some a dynamics or Lindbladian. So I think this result is really a beginning of kind of exciting systematic classification of the mixed state phases. So yeah, let me conclude here. Thank you.
Questions?
Very cool talk. Thank you very much. So the first thing is just a very quick semantics comment maybe. Maybe it doesn't make so much sense to call it an axiom if it's sort of violated all the time.
Right. Yeah. So approximate axioms then maybe.
Yeah, or condition. I don't know.
Yeah,
but
conditions.
I
call it axiom because the pure state study, they call this axioms. Okay. So we are using the language, but I also am aware that the axiom is a bit inappropriate.
So the other thing, I would have thought the natural notion you should explore, and you haven't mentioned this at all, is gapped local Lindbladians. Like there you have a gap and everything, and you have a parent Lindbladian.
Mm-hmm.
Why not look at that?
Okay, first of all, Lindbladian is kind of, okay, I mean, as I said, I wanted to study starting from just the density matrix. If someone throw you a density matrix, I'm trying to look at the density matrix without referring to a potential like a parent process. But yeah, indeed, that's what we want to do. Whether this kind of classification, once this condition is met, whether there exists say gap rapidly mixing local Lindbladian, that's like really good question. But it's also at the same time pretty pessimistic, because if you, for example, have a toric code satisfies all this axiom nicely, but it does not have a rapidly mixing local Lindbladian, right? Because you need like a Fabcell circuit to prepare it, right? No matter whether it's a like channel or unitary. So even if these three conditions are met,
the gap doesn't imply rapid mixing, but I don't know, you still have the parent Hamiltonian in that case, right? So you could say for pure states, you still take the Hamiltonian, for mixed states, you take Lindbladian. But I'll let the others ask questions.
Okay.
Thanks for the stimulating talk. Quick question about maybe a definition. So when you said no long-range order in one of the axioms, that's
M1, M0.
So that's even in the case where you don't add symmetries, right?
So okay, so then when we have a symmetry, then we are like modifying it that like the violation is a constant plus exponentially small like tail in some sense.
So when you don't have symmetries and you say you want to rule out long-range order, what kind of state do you have in mind? Like
for example, you can have a state like the mixture of the like a zero incoherent mixture of like zero, like a many body 0 and many body 1.
Oh, I see.
Yeah.
It's that kind of.
Yes, yes.
I see.
Because like then without symmetry, this mixture is really arbitrary, right? So then like violation of the M0 can be continuously tuned. But now when you have a symmetry, like Z2SSB, this violation will exactly give a log 2 in the like infinite limit.
So maybe just one quick follow-up. So in the pure states, there is no analog of this condition.
Oh, like a correlation length is basically analog of this condition. Like zero correlation length.
Yeah, but that's like the difference between strictly zero and a finite correlation length. I thought here you were trying to rule out like long-range tails or some kind of.
I'm allowing long-range tail. So exact fixed point will not have a tail.
Yeah.
But I'm also like promoting this to only approximate conditions. Then I'm allowing exponential tail, and that's like finite correlation lengths.
I see.
Yeah.
Yeah. Thanks for a very nice talk. Maybe a follow-up to Daniel's question about Lindbladians. I guess the connection between gap and mixing time might be complicated, but if naively, I would have thought if I just take this like construction based on short depth local channels and kind of rephrase that as finite time order 1 time like local Lindbladian channels generated by local Lindbladians. And I might have naively thought like what you talked about should carry over. Like, is that correct, or is there some subtlety in that kind of?
Yeah. So like under finite local Lindbladian evolution, when I truncate them, I don't want these conditions to be violated much at the boundary.
Okay.
Yeah.
But apart from that, then like this should all holds for Lindbladian.
Yeah, I mean channels are just probably more general version of the like Lindbladian evolution, I guess, right?
Yeah.
You can always think of channel as a finite time Lindbladian evolution.
So perhaps the question is more about the tails. Like if you have a continuous evolution, then they're not like a strictly local circuit. Like
it's fine because like here, although I started from the fixed point conditions, I want to promote to explore the phase of matter. Then I allow these conditions to be violated up to the degree such that like this violation is for, let's say this like partition size I'm consider is R, then I allow the violation to scale exponentially small, like exponentially with R.
Okay. Yeah. Makes sense. Can I ask maybe a quick clarifying question? So in the first part, like the conditional mutual information that should incorporate both classical and quantum memory, is that correct? Yeah. And I think you talk about this, but I don't fully understand. Like this formalism, like does that help one like distinguish between quantum versus classical memory? And you talk about this like 4 gamma, 2 gamma distinction.
So from the state we can tell whether the state encodes a classical information or quantum information.
But you have to like look at the actual state, like
Yeah, we have to look at the state. Not only that, we have to do lots of processing of it.
Yes.
But yeah, we can tell still in principle.
Thanks.
Thanks for the interesting talk. I'm also have the same questions because we actually have an attempt to understand these non-equilibrium phases of matter through really studying Lambdalian and their steady states. But you know, when you say these mixed states, it's more like high-level questions, right? So what is really non-equilibrium about this? Is there anything that is
non-equilibrium in that equilibrium state is e to the minus beta h. The general setup state I'm considering is not e to the minus beta h. That's it.
But
I mean, that's the only thing about equilibrium, right? That it's e to the minus beta h.
Well, I wouldn't go. Okay, so what if you're? I mean, okay. I mean, I wouldn't call that non-equilibrium, right? Because when we talk about non-equilibrium, I think about dynamics. You know, you have things that you're right that eventually the state is not thermal when we're coding, but there should be some associated dynamics that I can picture. And then I guess my high-level question is that do you think that these kind of classification using these equivalence quantum channels and or your more refined versions of this, in some sense, would it give us anything that's new that we don't understand in the pure state classification quantum phases of matter, or it might actually in some form actually correspond to some reduced subsystems of maybe high dimensional classification which you already understood?
Okay, so this classical topological loop state is in some sense not like theory of anyons, because when you have a theory of anyons, you should have an anyon. There's something called braiding non-degeneracy saying that whenever you have an anyon, there's something that braid non-trivially. But when you have this like topological mixed state, you have some more general set of anyons where it can just braid trivially or not. So, but okay, in some sense that's just like a classical loop gas. So people were kind of understanding in a different way. But maybe one of the advantages of this framework is that it's incorporating this different classical and quantum concept into the one single framework and allowing you to do a systematic classification. And regarding your question about whether this is giving a new classification, I'm actually pessimistic about it because I think double space formalism was actually at least giving all the qualitative picture properly. And from the double space formalism, all the non-trivial features are kind of coming from the pure state physics. Or it's a degraded version of the pure state physics, right? And I'm actually on that side. And I think this framework is making that idea sharper. Because although we are thinking in that way, there is no rigorous answer, right? And through this framework, I'm hoping to answer that that's indeed the case rigorously.
I see. Thank you very much.
Pablo?
I was pretty much in line of the previous question, but perhaps let me make it the emphasis a bit more. So usually when I think about non-equilibrium, I'm thinking about I'm allowing to drive the system. I can have a dynamical stationary state with a lot of fluctuations. I can think of, I don't know, driven, I don't know, some MBL physics out of equilibrium. And many of these examples at the end, like finite depth, quantum channels, and these are some stationary states. Do you think since this is kind of focused on the topological part, and usually when we go to out of equilibrium, these properties are not easily realizable?
That's a great question. So, I was thinking about this question. So when we talk about non-equilibrium phase of matter, depending on how, again, it's really depending on how you define the rule of the game, right? For example, Floquet topological order, you need to know that like a Floquet unitary to talk about phase of matter. You cannot do a classification just based on the one snapshot of the state. So here, the game I was trying to play is, okay, if someone gives you the density matrix and asks you to classify, it can be some state that's under the non-equilibrium process, so not captured by e to the minus beta h. But at certain time, like it will evolve, as a function of time, it will undergo some kind of transition behavior, losing some information, or maybe after some TC, you're not able to decode what state you initially prepared, right? So that's kind of thing I wanted to answer, and at least this is answering that. Regarding, okay, more generally, like if you want to classify the dynamic itself, then I think that's the different question. And then the question you can ask is, okay, like if there's a dynamics and steady state, if there's a kind of one-to-one correspondence, if I'm trying to classify steady state based on this framework, does it allow me to classify the dynamics as well? That's an open question.
Should I include time then in these actions? If I really want to describe non-equilibrium phenomena, should that somehow include time in the formulation? Like how the system is stationary but with fluctuation? Do you mind? Okay, I can ask later.
Okay, well, let's talk it later.
All right. Maybe Shubhani, a really quick question while Jacopo sets up.
Yeah, a quick question about whether these axioms will change with dimension, because this is...
No, okay. Oh, so I didn't talk about, so higher dimensional generalization is very quick. You just like rotate the partition. So now you're splitting the local partition into balls and shells, or like top shells. So higher dimensional generalization is straightforward, and there's a worked out 3D example in the paper.
But like the ABCD partitions, like, don't you want to consider more complicated partitions? Will that not give any more interesting phenomena?
That's possible, but from what they think, we don't need to consider more complicated partition. Okay. The difference is that topological entropy, you have to consider there is multiple different partitions, which now start diverging, which was the same in the case of pure state.
Thanks.